PhD in Kyushu University. And after that, she had a quite long path in Japan at the level that yesterday I was having a headache to reconstruct the full path, and she made a map, right? Yeah, a map to explain. But so she was a special postdoctoral researcher at RIKEN, and if I remember well from my memories of East Asia,
it's correct.
RIKEN is an institute famous for interdisciplinary research, right?
Yes.
Also, yeah. Then she was an associate researcher at Keck, an associate professor at Nara Women University. Then she has been, up to 2017, an associate chief scientist at RIKEN again. Then from 2017, she became a professor in Kyushu University first and Tohoku University finally. And from 2017 as well, she is the director of the Strangeness Nuclear Physics Laboratory at RIKEN. She received also several awards. Among them, I noticed the 2013 Saruhashi Prize for developing computational methods for precise solutions of quantum n-body problems. And so she's an expert in computational nuclear physics with an emphasis on computational methods for few-body systems of nucleons. And today's talk is about that because it's about the Gaussian expansion method and its application to nuclear physics. Emiko, the floor is yours.
Okay, thank you very much for the nice introduction. And actually, the to visit in Brazil is just this time 4 times, and 2 times in Santos, and the 3rd time is just last year to stay in Tobias Press and San Jose do Campas. And so this year to stay in São Paulo is the first time. Yeah, like this. And I really enjoy stay in Brazil. And you see, because in Brazil, there are many in Japanese like a face person, right? And you see, my face also like a Brazilian. But unfortunately, I cannot talk about Portuguese. Maybe next time if I come here, I need to learn something more Portuguese. Yes, please also help me to teach me how to speak in Portuguese. Okay, so now I give a talk about my method for the Huberty calculation and its application in the nuclear physics. However, and it's just warming up, and maybe because you have a lot to lunch, right? So therefore, and quickly you are sleeping. So therefore, to avoid sleep, let me introduce myself. Here is the Japan map of the Japan. Have you been to Japan? Jesus and you're there. It's also in Brazil and also in Japan. It's almost opposite side. So therefore, you can go this way is go through the United States to the Japan, or to go to the Europe to the Japan, all the equal, right? Always we need to take the 24 hours flight. So then just 2 days ago, I arrived at here. Then now my body is almost 2 a.m. and at the midnight. So therefore, and I'm afraid that during talking, talk and immediately to sleep. So if so, please wake up me. Okay, so in any case, then I was born here is in Japan has 4 islands. This is a Kyushu Island, almost the south part. This is Korea, and here is China, and this is Russia. And this is Shikoku Island. This long island is Honshu, and this north part, Hokkaido, like this. And then I wasn't born here. It's very close to Korea, like this. And here, and as mentioned by Chair, and I got the PhD at the Kyushu University, one of the most good and national university in Japan. And after that, I go to this and move to Keike as an associate professor and associate researcher. And I was here up to the 2004. And after that, I moved to Nara Women's University as an associate professor. You can see this is a Women's University. That means all the students are girl students, like this. But this is also national university. And I spent time for 4 years. And after that, I moved to RIKEN. And I have my own laboratory named by Stress and Nuclear Physics Laboratory, and up to 2017. And after that, I moved back to my hometown and became a full professor, and up to 2020. And after that, I moved to Tohoku. It's a north part. From it's this is Tokyo, and from here to go there, almost 300 kilometers away north to this Tohoku area. And now I have a position at the Tohoku University. Also, simultaneously, I have position at the RIKEN. So therefore, I have a two position. And sometimes I commute to this RIKEN by high-speed train. We call it the Shinkansen sometimes. And my husband is living here. Just so I'm living separately with my husband. But but this is good to have a position at the RIKEN, because if I go to the RIKEN, always I spend one night at the husband's place. Okay. So in any case, this is my life. So now, what is the Tohoku University? Maybe some of the people doesn't know where is the Tohoku University. This is my building, and very fortunately, and just 10 years ago, we had a metro. Then this campus is very close to the subway station. So therefore, from my apartment to go there, and after out of this station, and just walking distance 5 minutes later, and I can reach this office. It's very convenient. And here is the group, and the professor is me, and I have an associate professor, and one lecturer, and 2 assistant professors. This is our laboratory. And then, what is a RIKEN? And so Chair mentioned about RIKEN, and then RIKEN is a very good place. And you can see, RIKEN is one of the world top-level institute. And so that RIKEN has almost 7 institutes like this. And you can see, and everywhere we have such kind of branch. And I belong to this main Wako Institute, which close to Tokyo area. Then here is a picture of the RIKEN Wako branch. And in this Wako branch, and the president of the RIKEN have an office around here. So but you can see this is huge and grand. But this is not this place does not belong to RIKEN. It belongs to United States. Can you understand why? Because you see, 80 years ago, and we and the Japanese also fight with the United States, but that was beaten. So therefore, and still, United States governed this area to check the RIKENs. Because RIKEN has at that time has a very, and we started to have accelerator machine. So therefore, and United States Army think this is very risky. So therefore, after World War II, and this accelerator machine at the RIKEN was throw away the sea. This is not so good. But after that, okay, we are just shaking hands with Japan and United States. Then we allowed to construct the accelerator machine. So now we have at the RIKEN, we have big facility named by RIB factory, right? And then at the MSU, now FLIB also start to run, right? And we have a strong competition to have a very good scientist merit, like this. So this is a RIKEN. So, and here is at the RIKEN, there are many buildings like this. This is the main building, and many researchers there. And if we're interested in staying in the RIKEN, and we have also like this and guest room, then many people staying there and inside of the RIKEN. Okay. Also, Tobias stayed one time and guest room at the RIKEN to discuss with us like this. And I belong to the second floor at the RIKEN, this main building, and here is my room. Okay, and please do not look at carefully because this is my room and there are many things. Yeah, and I share with my secretary, and you see here is a seminar room because I'm theorist. So therefore, we need to discuss more seriously about the physics. So therefore, almost every month, we have a colloquium or seminar, and here we just discussing with a lecturer and also collaboration. So you can see, and this is very comfortable case. And also here is a postdocs or any staff members, so and and room. Now I have a 3 permanent staff member, and Pascal and Ma-san and Neo-san. You can see French and Chinese, Japan, very international. And here now currently I have 3 postdocs, also like this. Okay. So then you can see that also, and we have some Japanese, also French and Germany and so on. So very international. So therefore, in my laboratory and also public language in English, and we really enjoy discussing physics. Okay, so this is my introduction. Do you have any comment or question? Okay, so if not, let's start about my method, okay, Gaussian expansion method. Okay. My research is, one of my research and goal is to develop my method named by Gaussian expansion method, which is kind of a variation method using the Gaussian basis function. And this is, we take all the set of Jacobi coordinate, and this method has been developed by Kyushu University group, namely, and Kamimura, who is my previous former supervisor, and his collaborators, including myself. And this method has been high precision calculation of the various 3 and 4-body system, including exotic atomic system and light hypernuclear and so on. So from now, I shall explain this method in this seminar. Okay, so before explain about my method, and I just saw and tell about you and general things, because I just say many important problems in physics can be attributed to solving accurately this Schrödinger equation for the 3 and 4-body system. And by solving this equation, we can predict various and observable before the measurement, and we can obtain new understanding by comparing the observed data and our theoretical prediction. So for this purpose, it is necessary to develop the method to calculate a 3 and 4-body problem very precisely and to apply the various fields such as nuclear physics as well as atomic physics. So what's happening? Okay, in atomic physics, now so the 2-body system means the atomic physics and atom is composed of the nucleus electron. Now this is a 2 particle. Therefore, we call it this is 2-body. And this is a 3-body, that means nucleus and 2 electrons, like an helium atomic system. And here is like in hydrogen atomic molecular step, because like a 2 proton or electron. This is the typical 4-body system. So, and in this way, in atomic physics, constant particle electron and nuclei. But the mass of electron nucleus is this kind of relationship. And also, any Coulomb interaction is relatively weak. Therefore, for example, using the adiabatic approximation, and we can perform the 3 and 4-body calculation more easily than those in the case of nuclear physics. What is the nuclear physics? Now here is the nuclear physics. That means, for instance, nucleon and proton, it's a kind of 2-body, and here is tritium or alpha particle. So in this way. However, in nuclear physics, since the interaction between nucleon and nucleon is strong, right? So therefore, we have no approximation method to solve the 3 and 4-body problem accurately. Then we should develop the method for the solving various Hugh-body problems accurately. So therefore, and in order to calculate such kind of Hugh-body problem, so far I have been developed this Gaussian expansion method. So what is this? So for instance, in order to solve this Schrödinger equation, we use the Rayleigh-Ritz variational method, and we obtained eigenvalue, this E, and eigenfunction psi. And here, we expand this total wave function in terms of set of this and basis function. Okay? And this Rayleigh-Ritz variational principle leads to the generalized this matrix eigenvalue problem. Then here is also an energy and overlap matrix element given by this equation. Then next, we get the eigenenergy E and coefficient C by solving the generalized matrix eigenvalue problem. Then, after that, we can get the set of this psi wave function and set of this and eigenvalues. Okay. So this is a generalized how to solve the Rayleigh-Ritz variational method. So now I shall expand about my method. So for simplicity, and I shall expand about in the case of the three-body problem. Now, in order to solve the three-body problem, then we take these three kinds of the Jacobi coordinate. And so we should solve this Schrödinger equation. And now, Hamiltonian can be written by this equation. And this is a kinetic energy. And this V is just potential between this composed of two particle potential. Okay? Okay, so this is just and we call it a channel, just numbering of the Jacobi coordinate.
What's the Jacobi coordinate?
Here is just in alpha and 2 and 3 in just small r1, and also here relative coordinate capital R. So because here is just we define, and if this capital R is just going to the number one particle, then just we define that this is channel number 1. Okay, and here is just this capital R is going to the number particle number 2. Then just I defined just second and Jacobi coordinate.
Why do you use 3 different coordinates to describe the same system? I don't understand.
Because I will take about why. Okay, in principle, we can take the only one and Jacobi coordinate.
Yes.
Yes. However, and I will tell you the why. Okay, just next slide.
Okay.
Okay, so this is quite good to answer question, but just from now, and I will just tell why. Okay, but in any case, we take these 3 kinds of Jacobi coordinate, and so this wave function has a sum of this amplitude now. So then, each amplitude. Each amplitude are defined by this radial part and spherical harmonics for the small r, and this capital R is also a radial part and spherical harmonics. And for each channels, it describe this unknown coefficient and also small r, capital R, radial part, and spherical harmonics like this. But of course, I have such kind of coordinate. So then why? Okay, of course, and we can have only one that this is Jacobi coordinate. And however, in just a particle motion, is sometimes, for instance, we assume, and this particle and this one particle is strongly in binding, and if this particle is so long way, so then, before and solving such kind of motion, and no one knows which is better or not. So then, in order to, and so, how do I say, it's converge energy very quickly. And even if we have this kind of Jacobi coordinate, in order to get the energy accurately, we need to get more higher partial wave. For instance, here is J equal, for instance, and J equal 0 plus state. Then the summation of the small l, capital L, and we need to input in many angular momentum. For instance, this is L 0, 0, and 1, 1, 2, 2, 3, 3, 4, 4, something like that. So then, after solving the wave function, if this is the channel is very good. However, if we use only one channel, then this energy is not so and converges very slowly. And then it's very the CPU time is so larger. So therefore, it's not so good. However, if we take these three kind of the channel and simultaneously, so then that you can see if this channel is important, we already include this channel. Then, and if we have this kind of 3 channel, then quickly energy is converged very quickly, and to go to the exact binding energy like this. with a small value of the angular momentum.
So you're assuming that capital R is much bigger than small r, or what's the approximation you're using? I don't
Oh,
understand.
no. So here is just defined small r and capital R.
So they can be the same size.
Same size.
So how do you distinguish C equals 1 from C equals 2? I don't understand.
So that this is just and we have just 3 channels. So therefore, just a
Physically,
numbering.
why are they different channels? I don't understand why physically they are different. It looks like they're describing the same system. You're not changing the distances or anything. You're just describing it with 3 different parameters. I'm confused.
Oh yes. So then, so in this case here is just here is just a parameter, and then here is angular moment. This is radial part and spherical harmonics. And then here is we have just parameter. Okay. So then, in order to get the binding energy deeper, then we try to so this is a number of the basis function, and also range is just why I take the range as a geometric progression. And here is the number of the basis function, and also this first term, and also this ratio is just parameter. Then so we just put on this parameter to get the energy value. So therefore, after that, we don't know which is better or not. It's always a trial.
So in particle physics, I know sometimes you talk about different channels. You have S channel, T channel, U channel, where different things, different.
Yes, different one, yes.
But how do I distinguish? So normally.
Those are distinguishable here?
Yes, of course.
They're different particles.
So, but how do you tell if something is C equals 1 from C equals 2? I just don't. So the orange is not always orange? I don't understand.
Orange and yellow are different. Yeah.
But it looks the same to me.
Okay.
Yes. So is something decaying? I just don't understand.
One is different from two, different from three.
Yeah, but how do I know if I'm in, since capital R1 and small r1 can be any size?
Size
Just by
is,
looking at the picture,
yeah,
how do I say
because in the size is after having the very exact value, then after that we understand about this size of the small r and the capital R. And sometimes it's the small r is smaller and capital R is larger, like this.
Maybe I can comment.
Yes.
It's just to take the different asymptotic channels. So you can have 1, 3 bound, and then 2 far away.
But assuming that capital R is larger than small r.
Yeah, but
Similar.
to make
So sometime, yes. So it depends on the nuclei. Yeah. So therefore, just assuming, however, after diagonal Hamiltonian, then we got this kind of shape.
and mathematically, Fader also proposed that separation to take into account the asymptotics. Yeah. So then you are able to write down Lippmann-Schwinger equations like that has unique solutions in the scattering region. Then he made this separation, but physically it's just to take into account those possible asymptotic states.
So for example, considering the configuration 1, you are assuming that, let's say, 2 and 3 are the scatterer and 1 is the scattered particle, so to say?
Yeah.
Ah,
So
okay.
if
okay,
so,
that,
if the
okay, that makes sense,
yeah.
probably.
Okay, so then now important issue of this variational method is how to set good set base function. But so this is very important. What is a good set of the basic function? That means that using them, we can describe where the property of the wave function, it is a short-range correlation and long-range tail behavior. And also, we need to describe the high and oscillatory character. And also, second one is we can easily calculate the matrix element of the Hamiltonian is defined by this equation. Okay. So then, so just as mentioned before, then this Gaussian basis function for the radial part is very good. So now is here is new is 1 over this like this, and this is also first term, and here is A is ratio, and N is a number of the basis function. It's just parameter. However, this Gaussian basis function is suitable for not only for the calculation of the matrix element, but also the described short-range correlation and long-range tail behavior. Okay, so then that's all far, and always in Kyushu University group use this kind of the basic function. However, we have a critical problem because if the interaction between the constant solder in a particle is a central force, we can calculate the three-body matrix element very easily. Of course, but not easy for the beginner like us or master course. So then this method has been applied to the nuclear physics successfully. However, it is very difficult to apply to the three-body problem with a complicated interaction such as spin orbit force and tensor term. Of course, even the four-body problem calculation is very complicated. Why? Difficult. Okay, I will tell you. So just again I explained about in the case of three-body problem. Okay, so here just so let's calculate this central matrix element. So here is we can calculate just a central potential Gaussian part. Okay, here is we assume this we calculate this potential for this C equals 3,1. And here, ket part is we just put in C equal 1 case, and this bra 1 is a C equal 1, and ket 1 is a C equal 2 case. And so this C equal 1 case is this channel described at this in Gaussian function for the small r and capital R, and this in spherical harmonics. And also C equal 2 case is defined by this kind of the basis function. And then in just put in this calculation, but so we integrate out by small r3 and capital R3. If so, we need to make the transformation of this coordinate transformation. So now we should in here and make a coordinate transformation from the C equal 1 and 2. So here it's just because this is a Jacobi coordinate, then this alpha and beta mean the almost mass ratio, just a value. Okay. So then here is 1, 2, 3, and then just value, and we can just make a coordinate transformation defined by this equation. Okay, so then we can just put on insert this equation for here, and then now according to the mathematical formula, you can see that here we have two spherical harmonics, and if we insert this equation, okay. So then similarly for this spherical harmonics for the R2 and capital R1 and R2. So that to me, what I want to emphasize is that we have only one spherical harmonics. However, if we have a coordinate transformation, now we have two spherical harmonics. And also for the each, also we have after coordinate transformation, we have two spherical harmonics, and total we have 6 spherical harmonics. And also we have radial part, and here also if we insert this equation to this shoulder part of this exponential, and we got this part, then we have just 2 spherical harmonics. Therefore, after that, we have a total number of spherical harmonics. We have 10.
Sorry, can you go back
Yes.
one slide?
Here,
One more slide.
one more slide.
So we sum over small l and capital L. Is that correct? In the phi JM. I just want to understand the notation.
Here in the JM, you mean?
Yeah. So are we summing over all small l and capital L?
Yes.
Is that correct? In the definition of phi JM?
Yes, here is here. So this is JM is so this definition.
So we're summing over all.
That's right.
Yes.
Okay.
And the Gaussian function. Can you go back to the other one?
Gaussian function.
The slide that I was asking about.
Actually, you mean here?
You know the next the one.
Next one. Next.
I think what?
Here.
Keep going. No. You can. Oh, I see. So nu depends on n.
Yeah,
Okay. So you left it out, and then last slide
that's right.
you just didn't write the n. Is that right?
Yeah. So then here is
Okay.
just left it. Just I'm talking about this part.
Okay, I understand. So nu depends on n.
That's right. Okay. So then in case, just what I emphasize in the three-body problem, now if we have some full coordinate transformation, now we meet this and 10 at 10 and spherical harmonics like this. Okay. So then we need to integrate out and 10 spherical harmonics. Okay. I have a question. Can you calculate by hand this kind of things? Right? Every people say no. Yes, that's right. And then so I just still remember that when I enter the master course first, this is my task. And my former supervisor and request me, first, Emiko, you should calculate this one. Otherwise, you should go out. So therefore, and so first day, I should integrate out this part. Of course, it's a very headache, right? So then no. So professor, I couldn't calculate. Okay, so Emiko, you are so stupid. Okay, I will tell you how to calculate. Then one day, and so my professor is sitting next to me, and so he taught me how to calculate, and almost it takes 4 hours to calculate, and it's almost to get and in order to get the correct answer, it took 4 hours and almost 10 pages of the A4 size like this. Then after that, okay, maybe I start to quit the job like this. Yeah. So in this way, it's so and complicated calculation. And then so this is three-body case, but so that it's possible to calculate. How about the four-body system? How many spherical harmonics we have? 24 spherical harmonics like this. It's a hard task because also I just try to write this kind of a slide. It takes 1 hour to write this kind of slide. And then so in the case 24 spherical harmonics in four-body system, even for the expert to know how to calculate three-body system, integrate out, but it is a hard task. So therefore, every people doesn't like to calculate the four-body system. That is a very critical point. Okay. So therefore, I just think about, okay, in order to continue the research, maybe we should avoid to use the spherical harmonics. How should we do? So then I came to this idea. Maybe this is not so good. So therefore, I just propose one thing. This Gaussian function around the origin, we assume this kind of thing. Okay, and then this in a Gaussian function to the shifted for the three-dimensional direction. Then we sum up like this. Okay, mathematically like this. Okay, so this is a pure and Gaussian, and then shifted to go epsilon and d something and three-body and vector, then sum up. So therefore, if we have such kind of function, then we could describe angular dependence by sum up to the shifted Gaussian function without spherical harmonics, because this is pure Gaussian. So then, if possible, then...
But, sorry, this is an exact formula or is approximate? Is exact?
Next. Yes, exact.
And you determine this formula or?
Yes, we have, because if epsilon goes to 0, then mathematically equal. Okay, so I just show you and what happening. Okay, this is some construction of the ISGL function. Okay, this is example for the simplicity L equal 1 and M equal 0. And here is the exponential R and also spherical harmonics. It's a kind of, we have some factor, but like in Z, exponential minus something like that. Okay, so then this is if we figure out this is a figure. So then and in order to equal, we just saying we can use this kind of the and Gaussian function, and this is a z, and this is some minus epsilon and shifted, and here is a plus epsilon z, and just subscript. Okay, and in detail we can show up like this. Okay, and here is 1 over epsilon, and then also we can calculate this shoulder part in exponential. Then you can see this is a cross term of the this part. Then we can make a Taylor expansion of the each. Then we can get this kind of relationship. Then just subtract. Then we can get this kind of things. Then here is a higher part. is just a mixture of the higher angular momentum. So therefore, we should go to the epsilon goes to 0, then this higher part is just so equal to 0. And also, we can remind this part, but here is 1 over epsilon, then just cancel to each other. Therefore, we have this value. It's so that corresponds to this one. So in this way, and we have epsilon goes to 0. Mathematically, it's so that and equal to each other. In this way, epsilon goes to 0, then mathematically equal to each other. Otherwise, approximation like this. So then here is so in this way we can say, okay, this epsilon goes 0 is important, so the mathematically equal. Then here, in the case of the L equals 1 and 0 case, and now we have 2 terms of this shifted Gaussian, and also D is a shifted vector, is so shown by this kind of equation like this. This is just a simple example. However, for the any angular momentum of the L equal m, and using mathematical formula, and epsilon goes to 0, then we can. So this is some formula is like this. So then we can easily derive the shifted parameter of the C and the shifted vector like this. So then we can use such kind of a pure Gaussian basis function. Therefore, it is easy to calculate the matrix element. Okay. So the merit of using we call this basis function infinitesimally shifted Gaussian lobe basis function. So then just simply ISGL function is applicable for especially the nuclear physics with high accuracy. And also merit of this method is to calculate the few body matrix element very easily because pure Gaussian. And then also we can calculate the energy of few body bound state very precisely. And also we can calculate the wave function very precisely in the short range region and long range region. So then to show that our method can provide with high accurate energy and wave function. So in order to show up, we perform the benchmark test calculation for the ground state of the helium-4 using the AV8NN potential among the 7 different Hugh-body research groups. Now, so that this is already published in this paper, and I show you our result. Okay. This is the first page of this benchmark test calculation of the four-body calculation. That to me, that we should calculate ground state of this helium-4 case, and we use a realistic NN force. Okay. And here is number 1 is the Fadeev-Yakubovsky group, and number 2 is my group, and number 3 is a stochastic variation method, and 4th is a hyperspherical calculation, and 5th is a green function Monte Carlo, and so on. Okay, what's happening? Okay, just I show up just only this energy. Okay, this is the binding energy of the helium-4. Okay, this is the name of the method. And you can see this red line is my result. So please look at this energy among these 7 different groups. Okay, this is benchmark test. So therefore, before showing, we don't know how much energy we can get. Then you can see, and our result is a good agreement with each other because they are getting minus 25.9 MeV like this. Okay, using the NN realistic interaction. And also we calculate the wave function. It's also NN correlation function. So that to me, that's what we see that almost a solid line. That to me, our result good so among the 7 different groups. So in this way, for the ground state of the four-body state, we can provide the same number of the energy value and also together with a wave function. So then also just I show up the helium-4 and the ground state. But so also and in the case of helium-4, we have a lot of so excited energy like this. Okay, and this is a deuteron, which is lightest nucleus to have a bound state, and this is triton helium-3. This is alpha particle.
Excuse me.
Yes.
In the previous case, do you have a kind of analytic formula, a series of your result for the ground state energy of the system? Your result that you find is a kind of series of terms, sum of terms?
you mean the and basis function, you mean?
For the energy, just interested in the bound state, in the ground state energy, which you compare with other methods, right?
Yes, here, like this, yes.
Yes, but in your case, you have some kind of analytic expression. I mean, a sum of many terms.
Some of the many terms of the basis function?
Yes.
Yes, of course. Yes, so...
Is it a complicated formula?
Because, yes, so then and my calculation is a variational method. So therefore, we need to calculate the matrix element for the potential, right? Using the four-body basis function, right? So then for each coordinate, and we put on the more than 10 basis function, and so for the small r and capital R and rho. So therefore, for each coordinate, more than 1,000 basis function. And totally to get the energy, then I take the more than 20,000 basis function, like this. Okay.
What does it mean, NCSM? Because it looks that there is like 1% discrepancy with the method NCSM. Is it?
Here?
Yeah.
This one?
I mean, NCSM. No, yeah, there is.
Non-core shell model calculation is something, so there is a, I don't know, is some deviation for the error bar.
So because let's say, since the energy is lower, should I expect that that method is better? Or like lower energy means better because I go closer to the ground state, to the real ground state? I see.
Yeah, it's so, yes, that's right. So because, except for the Hwadev-Jakubowski method, they are almost a variational method. So therefore, if we increase it, the number of the base function, always just going to the exact value, right? So then the variation method is always, and it's a little bit upper than the exact value, right? Like this. So therefore, my case is just I stop to increase the number of the base function, but I just see that an eigen and eigenvalue the convergence within the 30 keV. Then I stop it like this. Okay, so then now, and I'm just saying helium-4 is so, and I focus on just the second 0 plus state. Okay, because helium-4 is the lightest nucleus that exhibits discrete excited state. Then this second 0 plus state at almost 22 MeV has the same spin, isospin, and parity as the ground state. Therefore, this state, excited state, should be quite different spatial structure in order to orthogonal to this ground state. This is very interesting. So also important question to be the answer are that is it possible to reproduce the energy on the first and second and 0 plus state simultaneously or not? Okay, so the old question clearly answer this paper based on this four-body calculation with our method. Okay, so in this work we took also again AV8 and an interaction and the Coulomb interaction between these two protons. And the use of the two-body force alone does not reproduce the observed binding energy of this triton helium-3 alpha particle. Then also we additionally employ the phenomenological three-body force to range this kind of Gaussian so as to reproduce those binding energy is defined by this equation. Here is the two-range Gaussian, and so here W1 is also minus this attractive part, and this is repulsive part. I take it. Okay. So then the use of this potential, now we successfully reproduce this in triton and helium-3 in ground state binding energy. And this is alpha particle is also ground state is in good agreement with the data. And also this is also an observed charge radius in helium-4. You can see also good agreement with the data. So how about the second 0 plus state? Okay, here is. And so now I just tell, and just a ground state, it's a good agreement with the data. And also here is this is experiment data, okay? And you can see our result also good agreement with the data in the case of second 0 plus state. So then in this way, and once so that I reproduce the ground state helium-4, and also I could simultaneously produce the second 0 plus of the helium-4 case. Okay. So now, so I just show up the application to the nuclear physics. Okay. So the latest isotope is nuclear physics is an hydrogen. Okay, this is experiment data. You may know that this is a deuteron and neutron proton, and this is a total isospin called J equal 1 plus state, and binding energy is minus 2.22 MeV with respect to this two-body breakup threshold. This is experimental data. Okay, so now and we can just change in the proton. This is the dineutron. What about this and the neutron? And in this case, due to the Pauli principle, and so that we have this NN, and in this case is so L equals 0 and spin equals 0, and isospin equals 1 case. And we know this is a no bound state. However, so we can just also add it to the 1 neutron. This is 3 neutron state. How about this 3 neutron exists or not? Maybe, and we know we might not have a bound state. But what about the 4 neutron state? And then so that we can just put on many neutron, and then so infinite number is neutron star. Of course, due to the gravity, it's a very stable. But we have a question: how many neutron makes bound or not? So therefore, experimentally, and they search the multi-neutron state, and to have a resonance state or and bound state for the almost 50 years before my born. So then, so I just show you the theoretical overview about it. Yes. So, and the theoretical calculation so far almost 20 years ago, and Argonne group and Stephen Piper, and they suggested that there would be the possibility to exist as a 4 neutron state, and as a resonance state at also 2 MeV above the 4 neutron breakup threshold using this realistic interaction in the green function Monte Carlo method so far. And then, interestingly, in 2016, at the RIBA factory, and so they reported some peak. Okay, this is a paper, physical review letter. Okay, so according to the experimental data, they reported like this. This is 0 means the 4 neutron breakup threshold, and they reported the energy is like this, and 0.83 MeV above this threshold. But we have this kind of systematic and also some error bar. So then, if we consider about this kind of error, then we have they reported this tetraneutron state from the boundary region to the and the resonance region, like this. It's a first measurement of the tetraneutron state in 2016. So now, motivated by this experimental data, we have the theoretical and homework. That means, can we describe this observed 4 neutron state using realistic and interaction or not? So then, after this observed data, there have been some positive or negative and theoretical result. Okay, I shall expand about the positive result. And according to these 2 authors, and they have some positive result. And for instance, this person, and they reported to the energy is almost 0.8 MeV above the 4 neutron breakup threshold, and the decay width is like this. And also using this green function Monte Carlo method, they also report to the energies around the 2 MeV above the threshold, and so gamma is like this. Okay, so according to the theoretical calculation, and no bound state, but some people pointed out to have some resonance state. And so that also this person reported not positive, not negative result. That to me, also they use the non-core Gamow shell calculation, And so that they can say that they scale to the two-body NN case to the, and so one is also almost so as it is, so the NN interaction, and scale into the twice attraction and like this. And if they scale to the twice attraction for the NN part, they have a bound state. That means this 0 means a 4-neutron breakup threshold. Then if the energy is below this threshold, that means we have a bound state. If just above, that means the resonance state. So then if so twice attraction, they have also state so the below threshold. That means they have a bound state. Then that's so that they make us so weaken and in the NN part, then going to down, and so if it's 1.0, and they have a resonance state. And finally, they reported that so that this 4-Newton state is 7 MeV above this 4-Newton breakup threshold, and the gamma is around 3 MeV like this. So therefore, the comparing with the experiment data, and this theoretical calculation is a much higher energy and broader width than the observed data. And also, and some also had a negative result, and I joined one of them as a so negative result. Okay, I will show you that's why so that this is a so negative result. Okay, so okay, let me introduce my method calculation. Okay, also in order to calculate the tetraneutron state, I use the AV8 potential and also in a phenomenological three-body force. Okay, and then here, okay, in the case of helium-4 case, okay, and the total isospin is like this. Okay, if we assume Z part of the neutron isospin part is -1, and the proton is a plus 1/2, then here is almost here is a TZ total isospin minus 1/2. Therefore, and this is three-body force for the total isospin called 1/2. Okay, so this is a helium-4 case. Therefore, and so in helium-4 case, I calculate the ground state helium-4, but phenomenological three-body force means always in the only total isospin 1/2 and dominated. However, and if we go to the so this tetraneutron state is total isospin equal 2, then this three-body force is a total isospin equal 3/2 state. So therefore, and so in order to think about three-body force for the tetraneutron state, always we should think about the 3/2 and three-body force. And in this case, and in order to study about tetraneutron state, okay, we use the same shape. Okay. However, and in the case of tetraneutron state, okay, and this and core part is just fixed. However, and the attraction part is just I use a free parameter. Then W1 is should be adjusted so as to reproduce observed 4-neutron state. Then what's happening? Then the observed tetraneutron state was reported from the bound region to the resonance state. So therefore, in order to obtain the energy position and the decay with gamma, we should complex scaling method, which is one of the powerful methods to get the energy pole like this. Okay, here is just for the coordinate space, and we scale it like this. Then after diagonal Hamiltonian, then we got this kind of energy pole. Then this theta is a parameter. Then if theta is going to around here, then the continuum state is moving. However, if we have a just pole, and the pole is stable with respect to the parameter of the theta. For instance, you can see here is we have a very stable pole. Therefore, an energy, okay, in this case is here is this axis is a real part of the energy, and this is a imaginary part, or correspond to the gamma divided to this part. So therefore, you can see here is, for instance, if we assume that this 0 means a 4-Newton breakup threshold, then here is a 6 MeV above this 4-Newton breakup threshold, and here is a 3 imaginary part. Then you multiply it twice, there are 6 MeV decay with. In this way, and we can get energy pole. Okay, this is an example. Then how much is how is my result? Just so I show up that's my result. Okay, this is the energy trajectory of the J equals 0 plus state of change in W1 is the 3/4 of the attraction part. And 0 means a 4 neutron breakup threshold, and this is a real part, and this is the imaginary part. And this blue value is a W1. Then so in here is an observed data region, and if we take the minus 38 to the minus around 30 MeV, then we could reproduce observed data. However, if we have a smaller value of the W1, and the energy is going up, and the decay width is larger. Okay. So in order to see more clearly, I show up this figure. Okay. And here is this one is the value of the W1 attraction part of the 3/4, and this is a 0, means the 4 neutron breakup threshold, and these are the energy region. Then if we take the minus 36 to the 30, then we could reproduce observed data. However, if we if we have a smaller value of W1, then energy going up, then the decay width quickly broader. So this is also the behavior. So then here, in order to reproduce the data of the 4 Newton breakup, 4 Newton system, we need W1 attraction is minus 36 to 30 MeV. So then now we should also notify, it should be noted that this W1 for the T equal 1/2 state is minus 2.4 MeV to reproduce observed buying energy of the helium-4 and helium-3 and so triton. Okay, and we can compare with this value. Okay, so here is this, so T equals 3/2 is almost 15 times the attraction we need to reproduce a 4 neutron state. So now we have a question. This W1 value for the T equals 3/2 is reasonable or not? So to check the validity of this and 3/4, we calculate the energy of the H4 and helium-4 with isospin 1 and lithium-4. Okay. So then this is experimental data, and we saw that hydrogen-4 and lithium-4 is just a resonance state. That means this is lowest threshold, and above this threshold, almost 3 MeV, and we have 2 minus, 1 minus. And here is also decay width, and decay width is so larger. And here is ground state is 3 MeV above this threshold, and the gamma is around 5 MeV, like this. So then what happened in my calculation and in comparison with observed data? Okay, so this is also W1, and this is energy, and here this is the lowest threshold. Then if the energy is below this threshold, we got the bound state. Okay, above, that means we have a resonance state. So then this and the black one is hydrogen-4, and this and the red one is helium-4 with isospin 1, and the lithium-4 is green one. And if we have a minus 36 MeV for the W1 to the 30, you can see and almost deeply bound state. However, experiment data is here. So then from this value, and if we use this and W1 to this value to reproduce observed data for the 4 neutron state, we have a strong binding energy of this nucleus. So this result is inconsistent with the data of the A equal 4 nucleus. So because this state, it should be the resonance state. Then conclusion is like this. In order to reproduce the data for the 4 neutron state, unlikely attractive 3-body force is required. This is our result. Okay. So this is a very negative result. However, after our calculation, also Deltuber calculate does the same things using the Fadeev-Jakubowski method. In his calculation is following. Also in the NN part, so singlet S0 and scaling factor. Then so also he tried to get some pole, but also he has a negative value because so if so that he has some twice or 3 times scale to the V1, so singlet SL, they have some bound state for the tetraneutron state. But if we go to the 1 or something like that, and so he had a no and resonance state for the tetraneutron state. Also, they calculate chiral EFT potential, also AV18 potential, and then even if so that he used a realistic interaction, he had no resonance state. Okay. And then after that, and he and Chris Green et al. And Kievsky, and so also they use the hyperspherical harmonics method, and so they use the same potential with mine, and so they calculate some phase shift analysis that you can see, and so if there is some resonance state, then this phase shift goes to some 90 degrees Celsius. However, you can see it's almost a smaller and phase shift analysis. From this value, and also they say that they conclude that no resonance state, okay, like this. So therefore, and we summarize that so the tetraneutron calculation, okay, these are author and these are positive conclusion, and these are the not so and positive, not negative, and we three have a negative and result like this. However, I was shocked to see in 2022, this is experimental data in Nature, and they reported some, you can see, peak like this, and very close to threshold. So then, and using the helium-8 beam and proton, and so 4 neutron state. So now also we have another and homework. How do we interpret this experimental data theoretically or not? This is a real resonance state or another effect. So then, and in 2023, and mainly, and our collaborator, Rimantas Razauskas, calculate this kind of reaction cross-section by helium-8 beam and proton and 4 neutron state. And using the AV18 and Malfitton, and also chiral EFT, and chiral EFT plus 3 nucleon and realistic interaction. And these are the values. So you can see that this 0 means the 4 neutron breakup threshold, right? And even if he used the two-body calculation so that he can get this peak like this. And so he could reproduce this value. So from this calculation, now we understand like this. We interpret this peak is also the emergent as also the consequence of the final interaction among the 4 neutron state, 4 neutron system and 4 neutron in helium-8 and projectile. What meaning? Okay, so like this. Okay, now so this is a helium-8. And the proton is being, and it just hit it alpha, like this. So then immediately this proton hit it proton very quickly. However, this in a 4 neutron and feel it, this in a final state interaction. So therefore, as a consequence, they have some peak, like this. This is some we interpret such kind of things. So therefore, what is the definition of resonance state? Because theoretically, resonance state means that so we should have some pole. However, if we calculate a 4 neutron state, then we have no pole, right? So, however, experimentally, they have a peak. So then we could interpret such kind of things, right? So then experimentally, it's a final state interaction. Even if we have some and we have some final interaction, we have peak. If so that they would like to say just a resonance state, might be resonance state. But mathematically, it's a kind of we have a no and a pole. So therefore, and if we define the resonance state is like a pole, then we don't have any resonance state. That is our definition. Okay. So then let me summarize. And now in this seminar, and I explained about my method and a calculation method named by Gaussian Expansion Method. And also, as one of the application, I'm explaining about, I reviewed theoretically about the 4 neutron state. However, it is difficult to have a resonance state with the NN realistic force. Then to interpret recent data of this peak near the 4 Newton breakup threshold, we calculate this and reaction and interpret that the peak and as a consequence final state interaction. So then, in order to understand 4 Newton state in more detail, maybe in 4 Newton state, we can, for instance, put on the proton, this is hydrogen 5. And we have also observed data on the hydrogen 5. So then what's happening about this hydrogen 5? And also we can put on the more heavier nucleus. For instance, we can add it to triton. This is the hydrogen 7. And experimentally, they have some observed data. Then we could solve some calculate and compare with this data. And also we can add it to more heavier core nucleus. Because this is some slide by Tobias. And so he recently got a very big grant using this slide. Then so also I want to get a more big grant than Tobias, but in any case. And you can see this is also the and nuclear chart for the lighter system. And we have many Newton-rich nuclei, especially the core plus 4 Newton state. Then so the in order to study about 4 Neutron resonance state and more clearly, we need to, for instance, study about this term in a core plus 4 Neutron state like this. Okay. So then we plan to study this nuclei in the future. Then so I will conclude whether or not 4 Neutron system exists as a resonance state or not. Okay, so thank you for the attention.
Thank you very much. Time for questions.
Hi. I'm not from the field, so can you, again, maybe you already said that, just tell me what are the assumptions behind your Gaussian expansion method?
Okay. So the Gaussian expansion method is, parameter is like this.
So it's an approximation, right?
It's a kind of, it's a variational method.
It's a variation. So the new parameters are the variational parameters?
Yes, so the variational parameter is here. Here. It's so
it's the new.
Yes, new is a parameter.
Right,
yes,
so new, so you solve for those. And then is it an assumption also that you're not considering 3 body interactions, because in the potential that you wrote in the previous slide, you just had a sum of 3 terms, so only 2 body interactions. Is that correct?
Okay, so you were talking about tetraneutron state.
Oh, no, it's the general, yeah.
Here
yes,
it is.
yes,
okay.
yes.
Yes, this is just showing up, but so that this is just so in order to see the very easily, that's I just show up. But also I can calculate more and some in function of the potential. Also I can calculate numerically.
Yes. No. So can you go one slide before this one? I think when you have the potential.
Potential is okay. So that means 3 by 4. You mean okay? I just understand.
Sorry
what do
about
you
that.
mean? Here, right?
No. No. I meant even in the very beginning, you had a potential with 3 terms, which are function R1,
okay,
R2, and R3.
What are you talking about?
Yeah.
Okay. That I understand.
Yes, exactly.
So
yep. This is an assumption that you're factorizing these interactions in terms of 2 body interactions?
Here is just so and just I put on the general term. So therefore, in this case, I never assume. Just so I got this, once I get some potential, then I would calculate something. So that, for instance, and for the atomic system, Coulomb interaction is only in atomic system, and potential is only Coulomb, right? Okay. So therefore, also
only 2 body interactions.
No, 3 by 4 also I calculate. Okay. Once I have some in 3 by 4 term, then also I can calculate.
Okay.
Because just so in integral out that matrix element.
So this is not an ansatz. This is
no.
Okay. And the other question is, you have to assume a potential also, right? For
Excuse
the nucleon term, you have to assume a potential. So that's another.
This is another
another issue.
Yes.
Okay. Thank you.
More questions?
So thanks for the talk. It was very good. I very like it. So my question is about the three-body potential. Like you write this one, there's interactions with two bodies, but then you put the three-body potential by hand, like
Yes, so yes, right. You're right, yes.
phenomenological.
Yes, in this case, it's a phenomenological calculation because at that time, and in this morning, I asked to Ingo and about what happening and t equals 3/2 information, right? So therefore, at that time in 2016, my calculation at that time, I didn't know how much the attraction we have the t equals 3/2. So therefore, so maybe this is just I decided to the free parameter. Then I try to fix the this value to reproduce a 4-neutron system if there exists, right? But this is just a free parameter. So therefore, after that, we check this value is so good or not. So therefore, using this parameter, I checked another system. It's also lithium-4 and hydrogen-4 because we have already observed data, right? So then, we calculate. However, you can see, and we never reproduce this value of the hydrogen-5, too strong attraction. So therefore, that is what I'm thinking about it. But after that, and many people try to calculate chiral EFT, and t equals 3/2 exactly included. However, they cannot reproduce the 4-neutron state as a resonance state. That is what point, of course. But in the future, now I'm starting and use the three-body force and using the chiral EFT because I already started and collaborated with Applebaum.
Okay, so I know this is phenomenological, but do you have a reason to put the potential like for 3 terms and not put a potential for like 4 terms? Is there something physical in this choice?
This is also, and I did, this is one of them. But also I calculated several versions of the three-body force for the phenomenologically, but the conclusion is the same. Okay, so that is what I'm asked to you, or a different question?
Yeah.
It's okay?
Yeah.
Okay.
Okay, we have another question here.
Thank you. I've got 2 short questions. The first question is like, let's say that you look at a tree-body, like a 2-neutron halo, like core neutron, and then there's like a p-wave halo, and you look at the ground state energy of that. And I was wondering, like, you do like the Jacobi coordinate thingy, and then so core as a spectator, neutron as a spectator, neutron as a spectator. And like for the asymptotic behavior, when you look at the 2-body channels, I don't understand like, you can reproduce, like the long tail behavior for a non-S wave type of thing with a Gaussian, because like
Okay, so then, in my calculation, and even for instance, you're asking me, so can I describe some long range tail? You mean?
Yeah.
Yes, of course I can do. Just so I didn't show up so density profile. However, if we have some hollow structure, then I could if I just increase the number of the basic function, then exact precisely I can plot and density profile and precisely. Yeah, even in the I just apply to the helium-4 bosonic system. In the case of we have a first excited states very dilute, right? In this case, I calculate the density distribution tail part. Then I understand almost 10,000 ohm strong. I could calculate very precisely the tail part like this.
And then I've got another question. At some point, you showed like the calculations at helium-4, and then you were looking at the you know, you did like this stability study of the resonance, you know, in the complex plane, you know, with the complex scaling, you know.
Yes, and
Complex
you mean
scale.
the helium-4 case?
So, you know, like this plus where you put like imaginary part of
Yes.
the, as a function of the
Yes.
real, and so,
This is tetraneutron state.
yeah, in my understanding, like when you do like complex scaling, you know that, you know, this angle is a parameter, and you look at the stable poles.
Yes, so
like
right.
the stable poles will be your
That's
real
right.
poles.
Yes, yes.
And my question is like, I thought there was a limitation on this angle. Like there is a lower bound for the angle that you know, when you do this complex scaling stuff.
I will show
Yeah.
you, okay?
And so I was wondering if there was like a limitation, like if you can tackle all the angles, like
Yes.
if you're not missing some angles because you cannot see them because there's a lower bound.
Okay, so that you are talking about just a
Yeah,
limitation of the
yeah,
theta,
yeah,
right?
yeah.
Yes, of course. So that, you know, here is so, you know, almost so the, you know, my method limitation is around so theta is so around 30 degree.
Okay.
Yeah, 30 degrees Celsius.
Like,
Yeah.
are you sure that there could not be a physical resonance like below, you know, like
Yeah,
in this
like this.
region there?
If so that it's a broad resonance state over the like this, it's so difficult.
Okay.
Yeah. So therefore, my calculation is theta is around two theta. No, theta is 30 degrees Celsius. So if we have a very, you know, a stable one, then I could get some resonance set. But otherwise, no, I couldn't get. Yes.
More questions?
I have a question about this ISGL function.
Mm-hmm.
So you show that there's this angle integration of the spherical harmonics. So in principle, you can, I mean, it's tedious work, but you can do it by hand. It would be a summation of a lot of Clebsch-Gordon coefficients.
Mm-hmm.
And
Yes.
suppose you can do that and make a table. Can you comment on the numerical efficiency with this ISGL function method?
So you mean that to get the C and shift vector? You mean?
So you can go back to the.
Okay, I will. Okay.
Yes,
it's
maybe one more slide before. Okay, go.
This one?
No, before that.
Before. Here.
Okay, so maybe one more slide before that. I think I would just the motivation of why to do that. Because you mentioned that it's difficult to calculate those.
This one?
Yeah, it's difficult to calculate all those spherical harmonics. But in principle, it can be done analytically, right? Into
So that means mathematical, you mean, right?
yeah.
Yes.
Because
But so yes, of course, once if we calculate that, we can use mathematical. However, even if we go to some three-body case, and for that we should calculate for the each and the nu is range parameter. Because in spherical harmonics and multiplied and exponent, and radial part, then so we should calculate for the each nu in range parameter we calculate. So then if we have if we use 100 basis function, we should calculate 100 times this kind of basis function. Then it takes some time. Therefore, we cannot use a mathematical. That is the point.
Okay, so it has a numerical advantage to use this ISG.
That's right.
Okay. Can I ask one more question? So about this helium-4 second 0+ state. So you show this level scheme is between this P triton threshold and neutron helium-3 threshold.
Yes.
So can you have you? Yes. So have you looked at the wave function and look at its density distributions?
Of course, yes. And this one, right? Yes. And then
how does it look like?
Here is dilute. That means 3 neutron and cluster, and 1 neutron is far away. Like this is the wave function. But in the case of here, this ground state is very compact. Then they have orthogonal to each other like this.
Okay. Yeah. But it's above this P triton threshold. Sorry. So is it a resonance above this threshold?
And experimentally, yes. However, in my calculation, is just isospin and representation. So that is why, and this 3n means I should average over this one. So then the average, and we have a bound state, almost 0.1 MeV below threshold. This is theoretical in a threshold.
Okay. If there are no more questions, let's thank Emiko again.